Alright, geometry students, it's Mr. Powers with section 5.2, which is about perpendicular and angle bisectors. Now, if you know anything about the Green Bay Packers, the year that I'm making this video, well, I just went to the retirement game for Brett Favre, and it was pretty awesome. So that's a picture of him when he got his jersey and everything retired. Um, but the goal, get back to what we're supposed to be doing here, the goal is I can use properties of perpendicular and angle bisectors. So we're going to use different properties of the perpendicular and angle bisectors. Make sure you have that goal written down, please, so you can self-assess yourself on that. We're going to skip ahead, though, to a couple of vocabulary terms. And the first one we're going to do, it says a point is blank from two objects if it is the same distance. So I think same distance or equal distance, that would be equidistant is the word. It's like a combination of equal and distance. Equidistant. Alright, that is our first term. Second one is a perpendicular bisector. And we've used perpendicular bisectors before. We've used angle bisectors. They're very similar. But a perpendicular bisector is a line, segment, or ray that is perpendicular to the segment at its midpoint. So it crosses through the midpoint of the line, the middle of the line, and it also is perpendicular to that line. Alright, so that's the second term. And the third one is a distance from a point to a line. We'll talk about that a little bit. If you're going from a point to a line, so if you have a line, you have a point here, the distance from a point to a line is the length of the perpendicular bisector from the point to the line. So we're going to fill in the blank here of the perpendicular bisector. The reason that is because if it's the perpendicular line, that is the closest point of that, or that's the closest distance from the point to the line is where it's a perpendicular bisector. So that's how you find the distance between a point and a line or a line segment. Alright, going on now. We have a few different theorems, so we're going to go through 4 of them. We'll do a couple of examples after the first 2 and a couple after the second 2. So the first theorem is Theorem 5.2. It's called the perpendicular bisector theorem, so it has a name to it. The perpendicular bisector theorem says if a point is on the perpendicular bisector of a segment, so if a point is on the perpendicular bisector of a segment, then it is equidistant from the endpoints of the segment. So if we have on our picture here, if RM is perpendicular to AB, those segments are perpendicular. Well, RM is a line, or PM, sorry, is a line, and line MA right here is equal distance from MB. Then we know that it is equidistant from, or then we can show that the P, that point, is equidistant from the two endpoints. So if we were to draw lines here, and like it is on the picture to the right, those two are also equal. Okay? So if it's perpendicular bisector of the line, and we're dealing with the point that is through that perpendicular bisector, then that point is also equal distances from the endpoints of the line, or the line segment. Interesting theorem there. Second theorem is the converse of that. So the converse of that is just going backwards. So if you have a picture like this, says if a point is equidistant from the endpoints, so if we have the picture where those two are equidistant from the endpoints, then it is on the perpendicular bisector of the segment. So then we can say that if we draw a perpendicular bisector, that point is on it. So it's perpendicular and it cuts these two parts in half here. Alright? So let's use those two theorems here. I've got 3 different examples. We'll do one at a time. First one. Actually, I'm going to give us some more room here. First one. Find the value of x. So if you know that these two are the same, we can use the converse of the perpendicular bisector, or perpendicular bisector theorem, to say that this is, n does go through the perpendicular bisector, so it's perpendicular, and that it bisects that side, so those two have to be equal. So then we know 2x has to equal 4. And when you divide both sides by 2, x equals 2. Alright, that's all we had to do for that one. Let's look at number 2 now. A little bit more to it. But now we have that it's a perpendicular and it's bisecting. So we know those are the same. So that means that it has to be, point H has to be equidistant from the endpoints as well. So we know that these two sides have to be equal. So we can set them equal. 2x minus 3 equals x plus 2. And when you solve that, you subtract x from both sides, a little algebra here. You get x minus 3 equals 2. You add 3 to both sides. To finish solving it, you get x equals 5. Alright, this last one. This last one looks the same, and we actually have it labeled that they're equal, and there's a perpendicular bisector. So we know that these two sides have to be the same as well. So 10x minus 3 has to be equal to that 5x plus 2. And again, when we solve that, subtracting 5x from both sides, 5x minus 3 equals 2. And you add 3 to both sides, and you get 5x is equal to 5. And the last step would be dividing both sides by 5, and you get x equals 1. Alright, so that is the first two theorems. Now the second two theorems, we're going to deal with angle bisectors. So angle bisectors, again, are very similar. They cut an angle in half, so the two angles this creates are going to be exactly the same. So this theorem states that the angle bisector theorem, theorem 5.4, which should be on your theorem sheet, hopefully these should all be going on your theorem sheet, says if a point is on the bisector of an angle, so we have point S here on the bisector of the angle, because these are congruent, that means that that is an angle bisector. Then the point is equidistant from the sides of the angle. So again, if we're looking at the distance between a line and a side, it has to be perpendicular of it. So that means that if, so our picture here, QS is, or it is bisecting angle PQR, and we know that those are, SP is parallel to QP, and SR is, perpendicular, is perpendicular to QR, then we know that PS and RS are going to be congruent as well. So they're equidistant from them. That's why we have those lines there. That's what that's what this theorem is saying. Now the converse of this theorem is very similar as well. If you know that, so it says if a point on the interior of an angle is equidistant from the two sides, so in our picture it's equidistant from those two sides, and again they're perpendicular, so we know that that's the distance between those two things, or the point and the lines, then the point is on the angle bisector. So you'll see it in the next picture, but it's going to be on the angle bisector of this angle. So QS bisects angle PQR. Excuse me. So it's just going backwards there. Now, a couple examples with this. It says solve for x. Now, if you look at this first example, number 4, we have, these are both 34.8 degrees, so those are congruent angles. If those are congruent and we're dealing with the perpendicular lines to this point, then these two lines, the distances between the line and the point, we'll say this is point x. No, that we're not going to use x because that's a variable that we're already using. We'll say that's point r. Then we know that these two have to be congruent, and that's from the perpendicular bisector theorem. So 3x has to be equal to 12. And when you divide both sides by 3, x equals 4. Now number 5 is going to be backwards. I can already tell you we're going to use the converse since we know that these distances are equal and they're parallel line or perpendicular lines, so we know that that's the distance between the point and the line. If those are equal, then the angles have to be congruent. So it makes it a perpendicular bisector or an angle bisector. So 4x must be equal to 2x plus 20. And when you solve that, you have 2x, subtract 2x from both sides. Sorry, that was an x. You have 2x equals 20, and then you divide both sides by 2 to get the x by itself, and x equals 10. All right, so when you plug that back in, both of those angles are going to be 40 degrees, so that works out nicely. I have one set of examples left. I think I'm going to save this for next time. So if you want to start on those, feel free. Otherwise, why don't you go ahead and answer the closing questions and try that error analysis thing. The error analysis are great because if you're spotting errors, then you really know the content. So error analysis and closing questions, and we'll see you next time.